Imagine a world where electric vehicles charge in just 30 minutes, where battery packs are 100% fireproof, and where mobility is not just sustainable but truly revolutionary. Meet Mr. Sheetanshu Tyagi, a relentless innovator on a mission to electrify the world. With experiences at companies like Ola and Rivian, Sir is set out to create something groundbreaking, from addressing fire safety and long charging times to extending battery life. He knew that building a truly sustainable future meant rethinking battery technology from the ground up. Join us as we delve into Sir's journey from the front lines of e-mobility to founding EMO Energy and explore how he's redefining the future of electric vehicles. So firstly, how did you get involved into the EV space?
Right. It's actually been a pretty long journey for me. It's exactly 10 years now since I really started my EV journey. So this is 2014. I was in Manipal, and we were trying to start, me and a few friends of mine in college back then were trying to start a company around rural transportation. So we're building like modified Jeep, which could also work as a tractor. And that's when I first came across Ather actually. So we were competing in IIT Madras, and I'd heard that there's obviously an electric scooter company there. And at the time, it didn't really mean much to me, but that's the first time the whole journey started for me. The startup, the rural transportation company didn't work out, so I moved to the US to do my master's, and that's where that really solidified. Because during my master's, I got involved with Ford. I was working on a couple of research projects on the Ford Marquis at the time. Started getting into modelings, controls, and simulations for some of them. And then that's where I was very clear that this is going to be pretty much everything now.
The Mark E was getting developed back in 2016.
2014, 15 actually. 15 is when it started. That's when a year or so of my life I'd spent in a research project. And then a couple of years after that, I moved around in a few companies. So there was Alta Motors, that was a startup at the time. RC Motor, that was another startup at the time. I worked quite a bit for both divisions there for engineering parts of it. And that's where this whole journey for me started. I was very clear that if the cost made sense for electric vehicles, and this is back almost like 7-8 years now, there's really nothing stopping it. It just is the perfect solution, right? Like from a mobility perspective, even now from an energy storage perspective, and the world's changed a lot in 10 years since then, but those companies really laid the foundation, right? Like so Tesla, Alta in the two-wheeler division, and then the really groundbreaking kind of thing that happened for me was Rivian actually, and that was literally exactly 5 years back when I left Rivian, but 2 years before that is when the whole R1T project had started. And I was fortunate enough to actually have seen the birth of the whole project from scratch. And it was pretty amazing actually, because from sketch to seeing tools come out, to seeing that entire vehicle become what it was and what it means now to the world of EVs in general is pretty amazing. And I obviously have a, let's say, third perspective view now because it's not there now. But the idea that that was what it was then and what it is now is pretty amazing to see. And the strength of what electric vehicles and mobility and alternate energy can do was really the foundation from those companies like Rivian, Ather in India, obviously Ola Electric, which I was fortunate enough to be part of then. It only takes a few people to really start moving this, right? Like through each country and each kind of ecosystem, let's call it. And yeah, I've, again, maybe just out of luck, maybe just not placed my bets right, I've been in startups which have actually succeeded quite well. And yeah, this started as a result of them meeting Rahul and kind of becoming what it is today.
Okay. And how has the journey been so far? Like, because I believe you started you were early into the battery industry.
Right.
So how has the journey been? And adding to that, how did you come up with the first prototype? Because that's always an interesting story of how a person comes up with his first product.
Yeah, it's a good point. So it actually takes us back maybe 4 years now, and that's actually when I pretty much met Rahul. This was day one of me joining Ola Electric. I was supposed to be part of the battery team. It was kind of an empty team at the time when I joined. They had just acquired Itergo. And the first day I met Rahul, in my mind, it was one of those things that we gelled quite a bit from day one. And for me as a person, the entire last 10 years of my life in general has been a pursuit to find a co-founder in general. That really has been most of my time I spent after my first startup, let's say 2014 didn't work. And Rahul compliments me in ways I felt was really what I wanted from a person, because there is a lot of understanding between us. There was a lot of, let's say, engineering management kind of work I like doing, but there's a lot of hardcore research he likes doing. So when we were at Ola, we were actually obviously talking out loud what the landscape is going to be, right? And Ola has been a huge driver doing two-wheelers the way they've been able to convince consumers like you and me to basically ditch Activas, to ditch motorcycles and buy Olas, and I'm one of them. The reality though is that this is just the start. There's only a few percent that we've basically been able to take as an industry and as in multiple organizations are doing it, right? But the reality is that if you take the ICE world in general, there's so many micro solutions. And now that India is moving towards, let's say, from 18 cars per thousand to, let's say, 33 cars per thousand to one day, hopefully, like 500 cars per thousand people. It's such a gigantic difference as a country that we see from today that Rahul and I always felt like there's going to be a large amount of energy and a large amount of overall scale we will need as a country. So batteries as a solution is something we were both involved in technically, but the reality is that from a limiting factor, from a obstacle perspective, implementation of energy in the electric vehicle sector is the only thing stopping it from scaling. Vehicles, a lot of companies make well. The overall implementation of chargers now I think is starting to happen. There's a lot of companies raising money, and I personally feel like there's a lot of work a lot of companies can do in charging, but the entire tech around building good battery systems at cost and at the performance you and I expect. Like let's say it should be able to do hundreds of kilometers on a motorcycle while doing high speed, while doing very good acceleration in 45-degree climates. These are problems today that motorcycles in the ICE world solve. But when Rahul and I were looking at this, nobody was really solving this for two-wheelers, for three-wheelers, let's say for odd segments like tractors, construction, machinery. Those are hard problems. Passenger cars today, a lot of the work from Tesla and a lot of the companies in China has been done. But that's where we started thinking that all these alternate sectors of mobility, all these alternate sources of energy which we're going to be implementing, like diesel gen sets, lead acid inverters, large scale, let's say wind and solar kind of buffer projects, only battery packs are going to let this happen. And the reality is that as a country, today, most large companies who will even set up cell companies are going to be China and Korea driven because they are so far ahead of us in, let's say, cell chemistry. And this is nothing against anybody who's working on cells, but the reality is that there is going to be a gap we're trying to cover there. But on a system level, if you take all the other aspects of engineering here, mechanical, thermal, electronics, electrical, firmware, software, integration of all of this, this is not something traditionally a cell company, or even for that matter, a vehicle company, or even let's say new age cell company who is trying to, let's say, set up a cell factory is going to be good at. True. This is a new modern form of systems engineering in a way, which Rahul and I then kind of expertise at also. So that became the starting point for us. How do we build out strong battery systems and how do we basically solve these like common problems, right? Which a lot of people solve in different ways. Safety, performance, life cycle. That's it, right? Like there are three words, we can solve this in 100 different ways, but that was a start point. So initially, actually, we thought that we basically solve this only from a software perspective. So Rahul has spent a decade doing, let's say, a lot of mathematical modeling, a lot of simulations, a lot of 1D, 2D thermal modeling to basically see how cells perform, how systems perform around it. And the limiting factor for a lot of, let's say, performance from cells itself, how do you basically extract the absolute maximum from cells? That we started to understand a few analysis techniques for. So the first 6 months, we spent building a basic battery pack, nothing special, but the software model we were able to develop was pretty advanced. The reality though is we started talking to a lot of different OEMs, a lot of different battery companies, and very quickly realized that the hardware itself, the infrastructure, the assets itself, were really not up to mark to where we felt the software was first going to optimize this. And that was really the first pivot point where we kind of understood that, you know what, we have to do the whole picture. And there were obviously a lot of other startups doing this at the time in different ways, and they still are. But the reality is that today there is a certain expectation now for what the asset should cost in the market to really scale to the millions, right? And that I'm talking about, let's say, the battery pack and the vehicle. It's an E segment. Now, today, if you basically take the absolute cheapest cells, let's say $50, $60 a kilowatt hour cells, then you can maybe build a system that you can actually sell to a consumer to get the cost right. But if you do that, then safety, performance, life cycle is bad. So how do you now build out the hardware, the mechanicals, the thermals, the entire software stack around those cells to basically say that, okay, now my final asset that we're going to be actually giving to a consumer whether it's as a sale or a battery as a service or swapping or fast charge, whatever it is, the absolute base asset in each segment has to be the absolute best it can get. And this has to be at the exact target price the market is expecting. I shouldn't be saying that, okay, so now that I can fast charge or I can do this or I can do that, here's a 10% premium. The market doesn't scale if that starts happening. There is an expectation that, okay, I'm getting this many rupees per kilometer. There's alternate fuels now that can get me this many rupees per kilometer. So if I'm going through all the hassle of converting to electric, to do all this charging nonsense, to find chargers, to connect, to do all of this, it's hard. It's not an easy ecosystem to deal with, right? Today, you need to be at that 0.7 to 1 rupees per kilometer standard. It has to happen. And we now finally have been able to take, let's say, the most basic, cheapest cells. Rahul and I basically built an entire battery pack, which was basically a two-wheeler battery pack. This is actually the one we ended up building, a much earlier version of this, with everything else from scratch. So we essentially went out, literally rented out an entire factory, took over that entire factory's operation. And that entire factory then spent a couple of months basically looking at different prototyping techniques, different manufacturing techniques, different connection systems, and a much, much more advanced, let's say, software-enabled BMS, which we feel now stands out in terms of what we're able to deliver, and at the expectation in terms of cost. So pretty much every single plastic piece, the metals, how we join it, the BMS parts, everything's from scratch at this point. And for the same size, for the same volume and the weight today in terms of life cycles and what we're able to give in terms of charging for that particular cost is basically unparalleled. And that's been the push, because now we're basically starting to scale this battery pack in the two-wheeler segment and also much larger versions of this in the bigger wheeler segment, essentially.
Okay. Well, when I was researching about the Zen pack, two things that I came across was that we claim that the Zen pack doesn't catch fire.
Sure.
How is that possible?
Yeah, no, absolutely, right? So I'll maybe explain what fire in this context is, right? And we have a lot of testing data and something we're going to be releasing soon to actually be able to show the advances of what we made in this, right? So the reality is there are 112 lithium-ion NMC cells in this battery pack.
Like,
One of them, for whatever reason today, is basically prone at some point in time to basically catch an internal short circuit, an external short circuit, or whatever that might be, right? There can be multiple reasons for that to happen. Now, you might have a manufacturing quality issue on the cell level. While you were handling the cell within the battery pack, you might have had an issue. You might have not detected some external, like, increase in IR in some way or in resistance in some way or the other. But the first step is to be able to detect that at the factory level and be able to see the change over time at a system level. So today, when we see this, and we see a lot of people doing this, they'll have hundreds of cells, but they're only monitoring a few cells. That we always felt, and Rahul and I both implemented battery packs with that kind of idea, right? That, okay, you only measure a few cells, you measure strings, whatnot. But that was the first thing we felt we had to solve. Like, how do you, even for a larger system, make sure you have temperature and voltage measured for everything? So today we have a couple of special plates we developed, which basically have as a piezoelectric in a system in the middle, which basically are monitoring temperature for everything. So if there is even a slight change in resistance for a specific cell, we can catch that. Now, once you've done that, the first layer of mitigation, you've basically been able to solve 90% of issues there. You can cut off the pack, short circuit that cell, the wire itself can blow out. There's multiple things you can do at that stage itself. So the temperature rise there itself might be limited. Now, the second stage might be that, okay, no, you've done all these things already. You've been able to cut off, you've been able to mitigate, you've been able to predict with all your software models, your neural networks, everything. All of that is happening today. But there might still be scenarios that one cell is going to blow up. One cell is going to basically either vent from the top or side rupture, right? There's two scenarios here. In both scenarios, we've basically been clear that there is a certain amount of energy that's being released and a certain way that's happening.
Okay.
From the top, if you're basically venting, the first thing you have to be clear is that the cells don't vent into each other. And there are a lot of architectures where you see that cells are stacked above each other or pointing each other. So one big thing we actually observed in our test itself is if we can face them opposite directions and we have opposite vent paths on both of them, so we have multiple vents in each corner of our battery pack, venting and pressure release is very, very key.
Okay.
So once your vent is opening up, how do you basically electronically control it? How do you know that, okay, this is happening, I need to be ready for this, and quickly release this cell's energy out of the system? because your entire objective within this is to make sure cells, energy, heat, everything doesn't transfer. You're trying to protect runaway. And even if one cell now is basically blasting open from a side rupture scenario, which is a lot more dangerous, and that is the really difficult one to solve for, right? The edge cases that we're basically as an industry always trying to solve for is side rupture. So a lot of people have different solutions for that. You might have barriers, you might have separators, you might have foam, spotting compounds, phase change, different things, right? All of those then impact weight, thermal performance, and just entire, let's say, operation of your battery a certain way. So we were very clear that we had to basically be looking at alternate materials and alternate ways to manage those materials to basically be able to absorb this, like say, one cell energy. So we searched a lot for this, right? Like we've essentially been through, I'd say, at least 50 compounds across the world for this.
Okay.
And it's not like we've settled on what we have for just because, oh, this is the best solution in the world. Today, we've basically used a certain dielectric coolant, which is a certain oil of some sorts, which we develop, essentially being circulated a specific way now. And the oil's energy capacity, the ability for it to absorb a certain amount of energy and then quickly basically release that into the vents is very critical. So we first tested multiple oils, we built one ourselves, we saw what energy it requires, what specific heat and energy absorption it requires. But very quickly we saw that if your fluid is stagnant, if it's not moving, there's a problem. So we redid the whole system, and now we have a very sophisticated flow system, which when, let's say, you're seeing the scenario that, okay, this cell's temperature is uncontrollably rising, but no matter what reason we've not been able to cut this off, we need to make sure that once the blast open, the energy has to get out and it can't spread. That today works very well for our system. So if there is actually a runaway scenario for us, very quickly you'll see at least 10 seconds of like slightly whitish gas come out. That basically is all of the lithium extract and some of the anode cathode that's separated out into your cells, along with some fluid quickly just leave one of the vents. So in every scenario that you basically see one or two cells bursting within the battery pack, the intent is to absorb that. Now, is your battery operational after that? No, we're not basically recommending that you have a fire-safe battery so you start using a vehicle, but the objective is that you're essentially trying to stop that intense scenario of a vehicle fire for hours, right? There is like literally reels around that whole concept, and like multiple WhatsApp forwards of thousands of vehicles, different vehicles on fire, right? Like, you don't want that show. Like, you want a safe burst of 10 seconds, the battery is contained, the vehicle is contained, the rider anyway is gone, it's not like they're under threat. But yeah, that scenario today, as a very, very high safety level, we genuinely are achieving. We have more than 1,500 batteries now on the road. We've literally had scenarios where a battery has been exposed to scenarios where other systems have then led to like short circuits or whatever extra scenarios on this from a fire exposure perspective too. And from each of those perspectives, we've come out pretty unscathed. The fact that we also use a full metal enclosure, all of those help because plastics then have their own issues and all of that. So yeah, the safety focus from the very start has been so strong for us that every decision, even if it increases cost a little bit or hits margin or whatever it might take to do it, happens. Because for us, it's very critical that this is not just some like low cost item that needs to scale. This is the most optimal, well-priced product which scales globally essentially after you start scaling.
So one thing that I could see that you have worked a lot on the software front. So could you please explain like the software of a battery? What does it do? What are the things that it's controlling? And how is it helping the battery in terms of battery health? Because that's again something that you have innovated on, that is improving the battery health of these cells.
Yeah, that's obviously a very critical part of the battery now, right? Because essentially if you take the system of an entire battery pack for, let's say, whatever application it might be mobility, it might be storage, there are unique requirements in each of those. Let's say a tractor for us when we're solving for is basically very high discharge. Like it's basically pulling 45 horsepower from a 30 kilowatt hour tractor. So you're constantly doing 1 point or whatever C rating, I'll come to that, basically at a very high ambient, right? So a battery pack's system is basically contained of the cells that you have, all your mechanicals that hold it together in whatever vehicle you might have. But the real work here is actually happening on the BMS, and that's the start point of the software, right? So you have a lot of hardware within your battery management system, which is basically measuring and controlling a few things that is essentially happening within your battery. So that's the first layer where software matters. You are controlling microcontrollers, you're controlling different ICs to essentially absorb certain amount of information from sensors. So you might have temperature sensors, voltage sensors, you might basically have a current sensor of some sort, you might even have additional kind of voltage is running, so you might have a 5 volts running somewhere, 12 volts running somewhere. All of this is the first layer of software. How do I basically analyze this data, convert it into data that's actually legible, and now I can do something with? With all of this data, what software initially is trying to do is basically just 3 things. Voltage, current, and temperature, I basically want control. And I want to be able to put my battery in a situation where I can safely control both ends of it, the highs and the lows. So over temperature, over voltage, over current cutoffs, under current, under voltage, under temperature. It's not under current, but under voltage, under temperature. Those are the first key layers a battery software needs to be able to solve for. Now, there is a lot of criticality, and obviously a lot of people have been able to solve this basic problem. It's a fairly standard, let's say, battery management system for you to be able to cut off based on these conditions. You need to regulate to this also, certify to these also, to a regulatory authority. But measuring and controlling these is the first part. And the second part obviously is when you're charging, discharging, controlling the currents. Like I might want an increase in current, decrease. All of that is basically the software's first function. Right now, most people stop here. Most people basically can control these, and let's say a second layer of safety functions, which you might have like a lot of, let's say, short circuits. You might have a lot of different controls for how current is flowing, and based on, let's say, ripples, based on different variations of your AC input for the wall or whatever it might be, you might be able to protect your battery better. That's the second layer of software now, which a lot of people are implementing. Let's say, I'd say like good OEM or a good battery company will definitely want to implement the strongest, let's say, safety systems possible. And today, the more sensor data you have, let's say, you might have a pressure sensor inside, you might have a gas sensor, a CO2 sensor, a NOx sensor, like all of these are obviously not standard by any means, but at the end of the day, the more data you have, the more your microcontroller can process, if you have large enough, and the more data you're getting to then control safety functions. This then brings to the last layer of the software, which is then understanding how your battery is aging. So this usually is obviously the most complex part, because not only do you not know the core chemistry of the cell, which the whole system is based on, you also don't really know what's going to happen after a year or 2 or 3 or 5, right? Like you'll get a lot of data from the cell company, you might have some historical data from somewhere, you might see research papers of what's happened, but India's supply chains linkage to the companies that we have in China and Korea, like it says the specific cells most companies buy, plus the variability of everything that happens doesn't guarantee you anything from a chemistry perspective, right? You might not really know what you're getting.
True.
So the third layer of software here is basically one that understands chemistry changes and what's happening to different cells that you might not just integrate from different companies, but from the same company. When you're buying different batches, are you really buying the same thing? Do you really know that will age the cell? You might have done a couple of lab tests on one cell. You might have done a few cell tests to see like, okay, I have a few data to like 80% or whatever it might be. But do I really know what I'm putting into my system? This third layer of software is generally something new a few companies globally are trying to solve for, right? So there's Breathe in UK, there's Glimpse, there's a few companies in India, there's a lot of good companies globally. Now trying to basically build out what in a nutshell is a battery life cycle management platform. So what that should do, and what the ideal battery software here will end up doing, is literally analyze every single cell's thermal map, resistance map, voltage map, know how it's going to change over time for cell level, and then basically be able to give you an output saying that, okay, I have actually analyzed every cell's degradation pattern based on all my magic understanding, let's call it that for now. And then basically predict that each of these cells are going to be degrading this different way. And those might, so if I designed a pack versus somebody else designing a pack with the same cells, we might have different patterns and maps of degradation within that system itself. How does the software detect this and how does it predict this? This is a very difficult problem to solve, right? Because there are so many factors involved here from a design perspective, thermal, mechanical, software, firmware, all of that, but also just again the chemistry perspective here. That software has become very key to our whole pursuit as a company, because the reality is that I feel like that understanding of how well cells perform at an individual level and then how well they'll perform at a system level can only really come from a battery tech company. Like the cell company obviously knows the materials and the designs of their systems. The vehicle company knows how to use the battery systems for power and energy that they need. But the layer in between here is basically looking at a cell and saying, how do I get the most out of this? For me, this is a black box. I basically need to see patterns of curves and data points and now build out a model to understand this. So today we essentially have a 6-person team that is studying not just hundreds of cells data on cyclers, but taking a lot of cycling data from labs, from our packs for different packs, and from at least I'd say 7 different vehicles on road. So different 3-wheelers, different 4-wheelers, our own batteries, all of this data, and we need very little data, and it's very important that we do this with very little data. Like with that very minimal amount of data from these vehicles, how do we now find patterns of let's say usage, where we can now classify, let's say the rider itself. Okay, this rider is aggressive, this rider is operating high ambience, this rider is charging too much, this rider, etc. And then form battery health degradation models based on all our cell understanding and all of those, let's say, layers we built. Combine that and now essentially become what I feel in the future will be very critical is an underwriting model for financing. How do you essentially give banks and different communities and different stakeholders the confidence to then look at this, right?
True.
So the commercial value comes from there, but the technical understanding for us and the expertise we're trying to form on cells itself and all the layers around it is the focus here.
Also, so batteries are not as simple as the software and then cells and then you put it into a vehicle. You need to have it integrated and test it.
Right.
So what are the tests that a Zenpack undergoes, and how is testing different for batteries that are not removable and for batteries that are swappable?
Right. So I'd say there's 3 layers of tests again that anybody performs or at least should perform. So you'll obviously get the cells first. So we do a lot of tests on the cells itself. We might just get cells reports on the company itself, or at least some charge-discharge tests, some aging tests, some like high current, and basically to understand cells' properties. We usually start with those. Those usually take only a couple of weeks, but they're very critical in knowing some very critical parameters of the cells, because we also have a lot of modules that run to basically understand these. So we do a lot of, let's say, it's called an HPPC test, which is like a high profile kind of test. You do a lot of high current, then to accelerated aging to understand that. So that is basically the start point for us. Then we build packs out of all those cells and do the first cut of the AIS 156 test, which is the government authorities test to regulate, at least in India. It is based on a few global standards in the past, and in my opinion is one of the best standards in the world for batteries at this point, right? There's only, I'd say, the Chinese GBT standard and maybe the UL 2580 standard that are competitive. But it is a very well laid out and almost a very aggressive standard to be able to meet if you really do it well. Like if you solve for everything that they're asking for correctly. So that there is the first point. So we'll do a lot of the electrical tests first. We'll test for the limits that I spoke of, like say the overcharge limits, the undercharge limits. We'll make sure our BMS is working. We'll make sure that at least all our basic electrical safety systems work. Because that's what you want. You don't want your pack overcharging for no reason. You don't want your pack going to deep discharge. You don't want it to basically hitting, let's say, 60, 65 degrees. So once we've solved for those and once we're confident that those work, we start then doing some of the more aggressive mechanical tests. So you have vibration, you have shock, you have thermal cycling. You start doing those and basically make sure the structure of your pack is right. And from this point on is where the fixed and the removable packs split out. So you've done your initial electrical testing, you've done your initial, let's say, mechanical testing. Now is the more aggressive impact testing, right? So drop is a big one for swappable packs. And the reality is, it's not so bad to just pass it, But in reality, in the field, for you to be able to drop something 6 times from 1 meter, it's a bit intense. And that really influences a lot of decisions I'd say a designer will make for a fixed pack versus a removable pack. So a fixed pack would just be like a plastic shell or a sheet metal shell that you're basically able to bolt into something or just keep there, and it doesn't really have that much, I'd say, impact loading on it. But a system like this is completely different, right? Like, you now need to be able to really isolate your cells from any kind of load that might actually hit. And this is like a 1G load, and we want to obviously be better than the test. So it's actually a lot more aggressive than that in terms of the actual load acting on it. So that's obviously a big one to be able to solve for. And then the last test, which applies to both, and then is the actual most aggressive one, is a thermal propagation test, where you heat a cell or overcharge a cell essentially for it to go into a thermal runaway, really induce that bursting of a cell, and basically make sure you can protect for it. And these, once you're able to solve for these tests, I'd say 80% or 90% of your work is done.